Lab 3 Orbital Motion of a Star Around a Black Hole Physics 2211 Section A. The goal of this lab was to expound upon the mass of a black hole in retrospect to a star in orbital motion by intertwining the fundamental principle with Newton's gravitational force law. In an effort to do this, V-idle was used to use predisposed position data and use that to calculate velocity and Fnet, all in order to modify Newton's gravitational force law in order to obtain the black hole's mass. It was shown that taking a backwards approach from position to the mass of the black hole was an effective approach, as we were effectively able to obtain the mass of the black hole. Once again, in this lab, the fundamental principle in Newton's second law was used in order to update the position and the velocity as the orbit of the star went around the black hole. The final velocity was calculated using the formula. The final velocity is equal to the initial velocity plus the net force divided by the mass times the change in time. Also, the position was constantly updated, with the final position equaling the initial position plus the average velocity times the change in time. The gravitational force was a key component of this lab. It was the force of attraction between the black hole and the star. Again, the formula that we used was the net force is equal to the gravitational constant times the mass of the star times the mass of the black hole, all divided by the distance between them squared. And what we did is we calculated Fnet. We knew what G was, we knew what the mass of the star was, and we calculated the distance between them, and we isolated the mass of the black hole on one side of the formula. And this is how we ended up with the mass of the black hole in the end. In order to calculate Fnet, we actually had to divide it into two components, the parallel and the perpendicular. In the formula, to calculate Fnet, the Fnet parallel plus the Fnet perpendicular gives you Fnet. And in order to do this, we had to use the momentum in order to calculate each Fnet perpendicular and Fnet parallel. Dividing the momentum into these two pieces leaves us with the derivative of the magnitude of momentum over time times the direction in p hat plus the magnitude of the momentum times the change in momentum over time. Additionally, the magnitude of the change of momentum is equal to the change in momentum over time minus the magnitude of the change in momentum over time times the p hat direction vector. These relationships were coded into V-idle in order to calculate Fnet. Upon obtaining position data, velocities were derived in order to calculate momentum. We derived these velocities using change in position over change in time. And once we derived two velocities, we were able to obtain the momentum. Then the momentum was divided into the parallel and perpendicular components to calculate the net force. Now let's move on to V-idle to actually see what's going on in the computational model. Here in V-idle, we had to initialize a few things in order to create the computational model. The star mass was set to 1.989 e to the 30 kilograms, while the black hole's position was set to the vector -1 e10, -4 e10, and 0 in the z direction. The time interval was 86,400 seconds, which accumulates to 1 day on Earth. Here, as you can see, we were reading the predisposed file, and using this, we use a reiterative loop in order to calculate the velocity from the data. Here is our second loop where we use to calculate the net force from the motion data. What we did is we found the initial velocity and the final velocity and the initial momentum, and the final momentum by calculating the mass of the star times the final velocity to get final momentum, and the mass of the star times the initial velocity to get the initial momentum. We calculated the star's change in velocity and change in momentum, and using this we did delta change in position over change in time in order to find dp dt. We set Fnet equal to dp dt, and then we calculated dp dt parallel using the formula that we saw in the slides earlier. Again, using one of the relationships that we saw earlier, we saw that the dp dt parallel is equal to Fnet parallel. Also, we saw that dp dt perpendicular plus dp dt parallel was equal to dp dt. So we modified this slightly, subtracting dp dt minus dp dt parallel in order to get dp dt perpendicular. And here, once again, we set dp dt perpendicular equal to Fnet perpendicular. This is where we updated the star's position indexed at IDX, which is the current track position, and we appended it into a list. Here we updated the star's position, and here's where we advanced the clock. Lastly, here's where we used our final formula in order to calculate the mass of the black hole. We modified Newton's force of gravity law in order to obtain the black hole's mass, isolate it, and solve for it. Here's our final 3D model. As you can see, as the star moves along, Fnet parallel increases while Fnet perpendicular is constantly pointing towards the star. Here is the Fnet of both forces once you add them together. As you can see, it is expected that the Fnet perpendicular would increase as it goes closer and closer to the black hole, and then slowly decrease as it gets farther and farther away, with a trajectory looking something like this. In conclusion, position data of the orbital star can effectively be used to create a relationship with Newton's gravitational law of force. In conclusion, position data of the orbital star can effectively be used to create a relationship with Newton's gravitational law of force and can be modified to calculate the mass of the black hole. In an effort to answer the first "what does it mean" question, dp/dt is the derivative of the momentum principle, and dp/dt can be calculated from the position data, while Fnet, on the other hand, causes observed motion and cannot be calculated directly. This means Fnet is qualitative while dp/dt is quantitative. The new black hole will have the same mass as the original due to the positions, velocity, momentums, and net force remaining the same, answering our second what-if question. This lab effectively showcased that Newton's gravitational force law and the fundamental principle can be used in order to go in reverse process and obtain a value, and in this case, mass. Thank you for your time, and I hope you've enjoyed my video.